Hi everybody, if you were with us for our last video, we wrote out some chemical equations, but we had an issue because it looked like the left-hand side of our chemical equation and the right-hand side of our chemical equation didn't really balance out. So that's what we're going to talk about today. We're going to talk about balancing. And balancing is a way that we can satisfy something called the law of conservation of mass, which states that mass or matter is neither created or destroyed. So we can't make new matter. What we can do is rearrange it in different ways. So for instance, we can't just make new sodium atoms, we can bond them with different sorts of things. And the way we do that and show that in a chemical equation is with these things called coefficients. So coefficients are whole numbers that we write in front of different compounds. And we do that because we cannot change the subscripts that we've written in chemical equations. And furthermore, if we write out these coefficients, we want to make sure that we simplify them once the balancing is complete, if it's possible to simplify. So to make sense of that, I want to go back to an example that we talked about in the last video. We wrote out this equation, and I drew some red arrows to indicate that we had one bromine on the left-hand side here, and we had two on the right. And that's not good. That's not okay, right? We need to somehow balance those out. So some of us might get clever and say, well, we have two bromines on the right-hand side. Why don't we just put a 2 right there? And if we put a 2 right there, now we have 2 on the left. And that would be all well and good, except now we've changed fundamentally this compound, right? It's no longer KBr, it's KBr2. And that's a problem because we know that potassium has a +1 charge and Br has a -1 charge, and there's no way that we're going to have two bromines with one potassium because it's not going to be a neutral compound anymore, right? So that can't be it. We can't do it that way. So what we do is we add something called a coefficient. Because we need two bromines on the right-hand side, I'm going to put a 2 here. So I haven't changed KBr, I've just said in effect I have 2 of those KBRs. But you're going to notice if I do that, I've now messed things up because I now have 2 potassiums on the left-hand side. So I now need 2 potassiums on the right-hand side. And likewise, I can't just come in and put a 2 here because that would not be KCl anymore. I'd have too many potassiums. But what I can do is write this coefficient. When I write that coefficient, you'll notice that I now have 2 potassiums on the right as well, so things are good. And furthermore, that took care of the last problem, which was that I had 2 Cl's on the left. I wanted to have 2 Cl's on the right, and so this 2 makes me have 2 Cl's on the right-hand side. And so we're balanced, and so all is well and good. So let's get some practice doing that balancing. You'll notice that there are some hints here. We'll talk about the hints as we balance. And before we do, let's just see how these coefficients distribute, much like they do in math class. So this 3 in letter A, this 3 operates on everything that follows it. So it operates on the n and the 2. So really what that means is that we have in this example, if we're counting up, we have 6 nitrogen atoms. In letter B, the 4 operates on all 3 of these things kind of independently, right? So in letter B, we have 4 hydrogens, we have 4 nitrogens, and we have 4 times our 3 oxygens. So we really have 12 oxygens. And then in letter C, things are crazy. So the 4 again operates on everything, right? 4 operates on Mg, but there are 3 magnesiums, so really we have 12 magnesiums. And the 4 also operates on the P, and the 4 also operates on the O, but similarly, this 2 is operating on the P, and this 2 is operating on the 4. So let's do the blue stuff first. We have 2 phosphoruses, but now we have 4 of this compound, so 4 times those 2 means we have 8 phosphorus. If we do the blue stuff first, 2 times 4, we have 8 oxygens in every one compound, 8 oxygens in every one of these things. But we have 4 of them, so 4 times 8, we actually have 32 oxygen atoms here. So we'll need to do similar things as we're balancing, and our goal is to basically get the same number of elements on the left and the right-hand side of these equations. And you might wonder, well, how is that satisfying the law of conservation of mass? Remember, based on the periodic table, iron always has the same molar mass, right? It's 55.85. And so if I have one iron on the left and one on the right, then they're both going to weigh 55.85. But there are 3 of these on the right, so it's going to weigh 3 times that. So I need to somehow get 3 on the left. We'll get there in a second. If we're new to balancing, which we are, we're going to recommend that you follow the following kind of tips and techniques, and then you can get away from this as you get more comfortable with balancing. But let's start here. Let's start by making a list underneath the arrow, because the arrow really indicates the middle of this equation. And I'm going to list out everything that is present in the equation. So there are irons, and on the left-hand side there is 1 iron, and on the right-hand side there are 3 irons. There are also chlorines. On the left-hand side there are 2 chlorines. On the right-hand side there is 1 chlorine. There are sodiums. On the left-hand side there are 3 sodiums. On the right-hand side there is 1 sodium. And there's also this PO4 group. Now, we could list out the P and the O separately, but one of your hints is that if a polyatomic ion shows up on both sides of the equation, which it does, here's a PO4, here's a PO4. If it shows up on both sides, it's actually much easier to keep the whole PO4 as a group and say, well, there are 2 PO4s on the right, and there's 1 PO4 on the left. And our job is to make the numbers for iron equal, make the numbers for chlorine equal, make the numbers for sodium equal, and make the numbers for the phosphate polyatomic ion equal. And so let's do that. You can start with any of them. We can start with the iron just for fun, right? Because it's at the top of the list, but you can start with any of them. We'll have more tips for which ones you should start with down the road. And remember, what we can't do is this. So we see here that there are 3 irons on the right. We can't just say, well, let's make 3 irons on the left, like that. Remember, you can't add subscripts. You can only add coefficients. So how am I going to change this iron? Well, I'm going to put a 3 in front of it, and that coefficient is going to change this iron to 3. But immediately change your list to indicate what else happened. That 3 also changed the chlorine. So there are no longer just 2 chlorines, there are now 6 chlorines on the left, and we're going to have to fix that in a moment. Okay, so don't just write the 3 as a coefficient, also write down what else has changed. So looking at our list, we're in better shape because iron now has 3 on both sides, so iron for right now is done. I'm going to check that off the list. Chlorine is next. Chlorine, there's 1 on the right, and now there are 6 on the left. So if there's 1 on the right, I need to put a 6 here to make sure that I have my 6 on the right. But check it out, that 6 also applies to the sodium, so I also now have 6 sodiums on the right-hand side. And we're going to have to come back and fix that. But this is a good thing because I got the chlorines a little bit closer to where they need to be. Let's deal with that sodium now. I have 6 on the right, I have 3 on the left. So what number can I multiply by 3 to give me 6? Well, I can put a 2 up here. And if I put a 2 up here, I'm going to get my 6 sodiums, but that 2 also applies to the phosphate. So now I don't just have 1 phosphate, I actually have 2. And you'll notice that adding that single coefficient actually fixed both of our last 2 things, right? Sodium, there are now 6 on both sides. Phosphate, there are now 2 on both sides. So as soon as you've made all atoms equal on both sides, you're good to go. And I don't mean necessarily that all the numbers top to bottom need to be equal, right? We have 3 irons, 6 chlorines, etc. What I mean is that on the left and the right side, for iron, they're equal. And for chlorine on the left and the right, they're equal. And for sodium, they are equal. Now, there's often a question. You'll notice there's a blank space right here. You may, if you'd like, write a 1 there to indicate there's 1 of that compound, or you can leave it blank. Blank and 1 mean the same thing. Okay, so you should get some practice with number 2. If you want to pause the video, feel free. Now, one little tip if you're going to pause the video. When you try letter B, one of our hints is to keep any element that's by itself for last. So notice, oxygen is by its lonesome over here. I know it's diatomic, so there are 2 of them, but save oxygen for last, because if we can balance out everything else, if we can balance out carbon and hydrogen, oxygen by itself is going to be really simple to just put a coefficient on the front to be done. So let's start by making our list. we know there are carbons on both sides. We know there are hydrogens on both sides. We know there are oxygens. On the left-hand side, there are 2 carbons. On the right, there's 1 carbon. On the left-hand side, there are 6 hydrogens. On the right-hand side, there are 2 hydrogens. On the left-hand side, there are 2 oxygens. And on the right, be careful, there are 2 oxygens in CO2 and 1 in water. So there's a grand total of 3 oxygens. So we're going to fix this thing up, and remember, we said we're going to save oxygen for last. So it's at the bottom of our list already. That bodes well. Let's fix the carbons. There are 2 on the left. We're going to put 2 on the right. We do that with a coefficient. Once I put a 2 in front of CO2, that makes 2 carbons, but it also changes the oxygens. And be careful with the oxygens, right? Because now they're in 2 different places. We have 2 times 2 is 4 oxygens, but we still have this 1 from water. So it's not 4 oxygens, we now have 5 oxygens on the right-hand side. That fixes our oxygens. Let's come back and let's deal with our hydrogens. So in terms of hydrogen, we have 6 on the left, we need 6 on the right. If I put a 3 in front of water, that gives me my 6, so that's good. And it also changes the oxygen. And there's a really big temptation for people when they change the oxygen here to simply come through and to take the number that we just wrote, which is 3, and add it to the number that we have here, which is 5, and get 8. But notice what happens. You have 2 times 2 is 4 oxygens right there. You have 3 times 1 is 7 oxygens right, 3 times 1 is 3. So 4 plus 3 is 7 total oxygens on the right-hand side. And again, if you said 8, then you made a little mistake, and the mistake was that you've already counted this oxygen once, right? So that oxygen has been counted once in the 5, and therefore we're only adding 2 more. But the simple way to do that is just reevaluate every time, right? Redo the multiplication every single time. So again, 2 times 2 is 4, 3 times 1 is 3, 4 plus 3 is 7 oxygens on the right. So we're in good shape because we saved oxygen for last, right? So now, as I said, all we need to do is put in a coefficient and we are done. But, bad news, you'll notice that I only have oxygen on the left and the oxygen is O2, right? There are always 2 oxygens. And I need to get an odd number. So I can't multiply anything times 2 and get an odd number. So this is where another trick comes in. There is a number that we can multiply times 2 to give us 7. And that number is 3.5, right? So 3.5 here does give us 7. If we do that, all of these are good. 2 and 2 are good, 6 and 6 are good, and 7 and 7 are good. But as you might expect, having a decimal as a balanced or as a coefficient in a balanced chemical equation does not work. So we can't leave that decimal. But there's good news. The good news is if you have a half, you can find a whole number to multiply it by that's going to give you a whole number, and it's going to make our life really easy, right? So what times a half gives us a whole? Well, multiplying it by 2. So what we're going to do is take every coefficient and multiply it by 2. Remember, there's a 1 sitting out here. I'm going to cross that out, and I'm going to make it a 2. I'm going to cross out this 3.5. I'm going to make it a 7. Again, just multiplying everything by 2. Cross that out, make it a 4. Cross out the 3, make it a 6. So if you multiply one thing by 2, you have to multiply them all by 2. And you can prove to yourself that these purple numbers work, right? So on the left-hand side, you have 2 times 2 carbons is really 4. You have 2 times 6 is really 12 hydrogens. And you have 7 times 2 oxygens is really 14. On the right-hand side, we now have 4 times 1 is 4 carbons. I now have 6 times 2 is 12 hydrogens. And I now have 6 times 1 oxygen here. And I have 4 times 2 oxygens here. So 4 times 2 is 8, plus my 6 is going to be 14. So this is actually 14 oxygens on the right. And if you look at those purple numbers, they all match up, 4 and 12 and 14. So we know that that balancing worked out for us because all of our numbers are equal. And we have coefficients. I know this is getting a little sloppy here. Let me just circle them so they kind of pop out at us. These coefficients they cannot be simplified, right? There's no number we could divide all of those by. So when you have coefficients that cannot be simplified and you've made equal numbers on both sides, you are good and you are done. So that's our next hint for you. If you can multiply a coefficient by a half, do it, and then double everything. All right, let's try putting that all together. Let's try writing word equations and then balancing them. So we're going to go a little bit faster through this. If you need to pause the video at any time, feel free. Letter A says solid sodium oxide. So what is solid sodium oxide? It is Na2O. Where's the 2 come from? Well, Na is a +1, O is a -2. You'll notice that I'm leaving a blank for balancing. It says that's being added to water. So added to water, H2O, at room temperature. And then it says it forms. That's where the arrow comes through. We're not going to include the room temperature in our equation. It forms aqueous sodium hydroxide. So aqueous sodium hydroxide, well, sodium hydroxide is sodium, which is Na. Hydroxide is OH -1. So those go together nicely, and that is an aqueous solution. And now all that's left is to balance. So let's make a list of everything that is on both sides of the chemical equation, right? We have sodiums on both sides. We have oxygens on both sides, we have hydrogens on both sides. You should always have the same elements on both sides. You can't just make elements disappear in a chemical reaction. So on the left-hand side, we have 2 sodiums. On the right, we have 1. On the left-hand side, we have 2 oxygens. On the right-hand side, we have 1. And the left-hand side, we have 2 hydrogens. On the right-hand side, we have 1. This becomes pretty darn straightforward, right? You'll notice that all of those are a 2-to-1 ratio. So if I put a 2 in front of sodium hydroxide, now I have 2 sodiums, but I also have 2 oxygens, and I also have 2 hydrogens. All of those are good, so we are completely balanced. Again, you can write in the coefficient of 1 in front of Na2O in water, or you can leave it alone as we have it. Just blank means the same thing as 1. All right, let's try letter B. So letter B, again, uses solid sodium oxide. So sodium oxide, we said, is Na2O. It is a solid. We are reacting it with carbon dioxide. Carbon dioxide is CO2. Carbon dioxide, we are told, is a gas, but we already knew that. And water vapor. So water vapor is H2O, but it's also in its gas form. Then it says to form, so there's our arrow, sodium hydrogen carbonate, which is a solid. Remember hydrogen carbonate. So hydrogen carbonate is the combination of hydrogen, which is H+1, and carbonate, which is CO3 -2. So that comes together to give us HCO3 -1. Bond that with sodium, what do you get? You get NaHCO3, and this is a solid. So we have a lot of elements to deal with, right? We have NAs, we have O's, we have C's, and we have H's. So let's make a list. We've got NAs on both sides, we've got O's, we've got C's, we've got H's. On the left-hand side, we have 2 NAs. We have O's in 2 spots. I'm sorry, we have O's in 3 spots. We have 1 here, plus 2 here is 3, plus 1 here is a grand total of 4 oxygens. We have carbons on the left, there's just 1. And we have only 2 hydrogens on the left coming from water. On the right, there's 1 Na, there are 3 O's, there is 1 C, and there is 1 H. Now, here's a recommendation, your last little hint. You'll notice that we had to count up 3 oxygens on the left-hand side. Save oxygen again for the end here, right? Don't try to start messing with oxygen at the beginning, because if you change any one of those three compounds on the left, you're going to change oxygen drastically. So let's change the other things first. You'll notice there are 2 sodiums on the left-hand side and 1 on the right. So we know right off the bat, we need to fix that. We're going to need at least 2 of these to deal with the sodium. But that changes a whole lot of other stuff, right? That also changes oxygen to 6. It changes carbon to 2, and it changes hydrogen to 2. So that one move was helpful. It helped out our sodiums, it helped out our hydrogens. They're both balanced. Now we need to change oxygen and carbon. And as I said before, let's save oxygen, right? Because we don't know which one of these will change. In fact, if we start messing with water, or we might start messing with Na2O. Na2O contains sodium, and sodium's already balanced, so we don't want a coefficient in front of that. And similarly, water has hydrogen in it, and hydrogen's already balanced, so we don't want to alter that at this stage of the game because we'll mess ourselves up. So what can we do? We can fix the carbons, and there are 2 carbons on the right. Let's get 2 on the left. So if I put a 2 here, I now have my 2 carbons on the left, but it also changed the oxygens. I still have this 1, plus 2 times 2 is 4. So 1 plus 4 is 5, plus this one is 6. I now have 6 oxygens, and bingo, that 1 coefficient changed both of those, and we're now good to go. Again, if you want to fill in coefficients for Na2O and H2O as 1s, feel free, but you don't have to. You can just leave those blank, and that means that there is 1 of each of those.